Today we are going to take a look at the basics of how COMSOL is used for acoustic structure interaction problems. I will walk us through some models to give you a chance to see the software up close and see how it might help you in your work. If you have never used COMSOL before and you want to learn how it works, my presentation today should help answer those questions as well. Hello everyone, welcome to our webinar on acoustic structure interaction analysis with COMSOL Multiphysics. My name is Arpad Forberger and I'm one of the application engineers at Gamax Laboratory Solutions. First, I'm going to give a quick rundown of how numerical simulation work in the COMSOL environment and what you can do with the software. After that, I will show you how it's done during the live demo. At the very end, I will mention some further resources where you can find more information, including full-length webinars that contain more technical details. Today's presentation is really meant to be a quick intro to what the software is, but we have many resources available if you are interested in learning more afterward. So here you can see what kind of examples can be solved using COMSOL Multiphysics. These are the so-called acoustic structure interaction demo examples. You can access them at our website freely, and you can download the models if you would like to try out for that. Okay, so various models include vibration and noise in a gearbox, so the acoustic field and the structure deformation and the multi-body solution is coupled together to find out what is the radiated noise in such a gearbox application. In the middle figure, you can see how a transducer is used for such purposes, and also it can be used for acoustic transmission loss calculation through an elastic structure. So it's another way how you can use COMSOL and an acoustic features here. So this is our current product suite. So just for you who have never used COMSOL, so what is COMSOL? COMSOL is a multiphysics modeling, simulation, and application design environment where all of the steps of a simulation are integrated into one user interface, from the initial setup to the solvers to post-processing to putting together a custom-built application. The COMSOL model allows you to couple together physical effects the way they are in the real world, which we refer to as multiphysics. The model we will look at today solves for acoustic structure interaction in a micro device, in a MEMS device, in a micromirror application. Once you have completed your COMSOL simulation, the software also allows you to create a customized app from the model, which enables you to deploy the analysis capabilities and results to collaborators, customers, or even colleagues around the world. And now what we are looking at is our current product suite. We have add-on products that can be combined with the COMSOL Multiphysics core package to enable simulation of specific physics phenomena across a range of application areas. These can all be combined with each other. We have modules for electrical, fluid, heat, mechanical, acoustics, and chemical simulations, as well as several multi-purpose modules and tools for interfacing with external software. COMSOL is very flexible. It contains many predefined physics interfaces, but also allows you to define your own custom physics and equations. Today we are going into the acoustics module features. That's the main goal here, to see how it's working in the real world, coupled to structure mechanics, since we are looking into a micromirror system that's vibrating and causing pressure variance over it. So these are the two modules that we are looking into today. Other application examples include transducers, from microphones through loudspeakers to MEMS transducers and even to flow meters. That's also possible to create simulation models and to create digital twin models for that one. Applications also include mobile and smartphones, headsets, hearing aids, and medical devices and instruments as well. Also, it's a wide range of application areas that can be coupled to automotive industry. If you would like to design mufflers or particulate filters, you can also use the built-in physics interfaces for such calculations, and also for calculating the interior sound inside the car cabin, and also for civil engineering and architecture. So if you would like to do some sound isolation and some transmission calculations, that's also possible to do that. And also with the pipe acoustics, so you can also use it for the noise, the radiated and the generated noise in the HVAC systems. Okay, so this is the product setup for the acoustics module, and what kind of physics interfaces and what kind of solver types and finite element methods are available in COMSOL Multiphysics. So we are in the free stream. The default and the widely used physics interface is the pressure acoustics physics interface. Three different methods can be used here: the finite element method, the boundary element method, the BEM, or discontinuous Gagliarkin finite element method. And if we are close to the boundary layer, which is very important for thin devices, for very small MEMS devices, you can also use to solve for the variations in the temperature field and the velocity field in the thermoviscous layer, in the boundary layer. That's the finite element modeling implementation. And also in the solid domain, you could solve for elastic waves in solids. And on the other side, so if you have a stationary background flow, so-called aeroacoustics, that's also possible with the finite element method that's implemented here inside COMSOL Multiphysics, or you can use the convected wave equation as well for such purposes. And again, for solids, the elastic waves equation can be solved either with the finite element method or with the discontinuous Gagliarkin implementation. Okay, so let's have a look at today's model. So we are looking into so-called digital micromirror device, which contains tiny, very small mirrors connected to each other. It can be used in projectors and in various applications. And we would like to use this in our model in a simplified manner. So these micromirror systems are part of small MEMS systems for integrated scanning micromirror systems in telecommunications and consumer applications. The mirrors have low power consumption and the manufacturing cost is low. Their applications range from microscopy applications, medical imaging, scanners, and heads-up displays to some fiber optics applications. The dynamic vibrating behavior of the micromirror, and especially the damping, is an important factor affecting the design of their actuator systems. In the development process of new micromirror systems, modeling the damping correctly and thus predicting the performance of the system can save both time and money. Okay, so a sketch of the idealized micromirror system is modeled here. So you can see on the figure on the right. The mirror is made of silicon and is surrounded by air. It's an 0.5 millimeter by 0.5 millimeter. You can see only the half of it, since a symmetry plane is used to reduce the computational domain here. And the thickness of the mirror is 1 micrometer. The solid mirror is modeled using shell elements, and the surrounding air is modeled using thermoviscous acoustics. A pressure acoustics layer is used to truncate the computational domain. The model combines the shell interface, the thermoviscous acoustics frequency domain interface, and the pressure acoustics frequency domain interface. So we are going to use 3 different physics interfaces to model such a device here. The 3 physics interfaces are set up and combined using multiphysics coupling, one for the acoustic thermoviscous acoustics and one for the thermoviscous acoustic structure boundary connection. One goal with the model is to get a correct assessment of the damping the mirror experiences. Therefore, the detailed thermoviscous acoustics is used to model the air domain surrounding the micromirror. The interface includes thermal and viscous damping explicitly, as it solves the full linearized Navier-Stokes continuity and energy equations implemented in the thermoviscous acoustics frequency domain interface. An important parameter in such model is the thickness of the viscous and thermal boundary layers. The model is both solved using a frequency domain sweep and using an eigenfrequency study. Okay, so let's jump into our COMSOL Multiphysics setup to see what do we have here. So this is our COMSOL desktop. To speed up computation, I have already included the parameters and the geometry. So here under the global definitions, under parameters, we have all the parameters set up. We have a closed evaluation for the viscose layer. This is called dayvisc. So this is the calculation of the viscose layer. So we will use the mesh node to correctly set up a fine mesh for the boundary layer in order to get accurate results for that one. Okay, so we have the mirror thickness, it's 1 micrometer, and we have some other frequency parameters that we would like to use during the sweeping process. So from the materials node, we have an air, that's the surrounding domain here, and we have the silicon, so this is the material for the micro mirror, so that's the setup here. From the mesh side, as we can go into the size 1 node, so here under this size 1 node we have added a restriction, upper limit to the maximum element size. So it's 1.2 times the viscose layer thickness in order to get a very nice representation and the resolution for the solution. So this is restricted, so we use the custom element size for that purpose. Okay, so we mentioned that we need 3 different physics, so let's add those 3 different physics interfaces. So first we need a shell interface, then we need a thermoviscose acoustics frequency domain physics interface, and then we need a pressure acoustics frequency domain. So from the acoustics branch, pressure acoustics frequency domain. Okay, so this is the 3 different physics interface that we are going to use. Okay, so from the shell we select the correct boundaries. We need only the shell boundaries, which is predefined in the shell node. So this is the shell interface assigned to the shell geometry node. Okay, from the linear material model we can go with the default settings, and for the thickness we can add that this is the edge underscore mirror. So this is the thickness of our shell here, and we need to add some boundary conditions in order to truncate the rigid body motion here. So we need to add the fix node, fixed constraint here at the back. So we fix our mirror at the back of the geometry, and we need a symmetry plane since we are using the half of it. So we need a symmetry boundary connection. Okay, symmetry, that's here in the front. Okay, and we need to add a load. So we go into the boundary load, face load. Okay, for these boundaries, and we need a total force user defined, yes, and in the z direction. Okay, so let it be x over 0.25 millimeter times 1 Newton over cubic meters. Okay, so this is our boundary load here. Okay, so from the shell interface, that's the only setup we need to make. So we have a symmetry boundary condition, a fixed constraint, and the phase load. Okay, from the thermoviscose acoustics, we need only domain 3. So here, this interior domain, so that's the vicinity of the shell, the little mirror. So here we are solving for the thermoviscose changes, so we need only use that one here. And we need also a symmetry boundary condition here, since this is only the half, this is only the half of the computational domain, so we need a symmetry boundary condition here, and that's all we need to set up here. And from the pressure acoustics, of course, we need only these domains, the outer domains. Okay, and we need also a symmetry boundary condition, symmetry here, and to mimic that there will be no reflections here at the outer boundaries, we can add a spherical wave radiation for such a purpose. Okay, and we need radiation, spherical wave radiation here, 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 and here. So this will mimic that there is no reflection from these outer boundaries to the interior of our computational domain. Okay, so that's all. So we already set up, and we need to couple those physics interfaces together. So here in the multiphysics node, we need an acoustic structure, an acoustic thermoviscose, yes, and the thermoviscose acoustic structure. Okay, so we can set it to all boundaries, so it's automatically assigned to the correct boundaries. So now the shell, the structural, is coupled to the surrounding thermoviscose interface, and now we need to couple the thermoviscose interface to the pressure acoustics interface. So we need an acoustic thermoviscose acoustic boundary coupling. Yes, that's where the two physics interfaces are adjacent, and that's all for our purpose. And then we can solve in the frequency domain. So we can sweep over the range of frequencies, and then we can also calculate the eigenfrequencies to see what's the node and the mode shape of the micromirror. So I already have a saved solution for that, so I can open up that one to look into the solutions. Okay, so here we have the displacement plot at different frequencies. If you go up with the frequencies, you can see how the displacement is changing. Okay, and we have one important thing to solve for the temperature variation, how the temperature varies at different operating frequencies, and the same goes for the velocity variations, the little fluctuations in the velocity field. And we can go to the displacement response, which is quite important for us. So here in the horizontal axis, we can see the frequency range from 10,000 to 11,000 Hertz. And here we can see the displacement of this point 16, which is here at the tip of the micromirror. So we can plot the displacement of this point as a function of the excitation frequency. Okay, so this is how you can set up thermoviscose structure interaction in COMSOL Multiphysics. So let's jump back to our presentation here. So you can find more in the application libraries, just search for it, and you can find lots of tutorial models and benchmark models for that. And also you can go our website to see what's possible there. You can find much more examples with detailed explanations, and you can visit the COMSOL blog. So if you want to read more details about how to do such simulations and what is possible in COMSOL Multiphysics, that's also a recommended way to read about these blog entries at comsol.com/blogs. And I thank you for your presence. And if you have any questions, feel free to reach out us, and see you at our next webinar. Thank you and goodbye.